All right. Well, let's go ahead and jump back in, everybody. Welcome back. Good morning, good evening, good afternoon. Thank you again for joining us and taking the time today for this day 2 of our training for flowsheet modeling in OLI Flowsheet ESP. So this is actually our first public training class for this course. We've done these in the past, but really focused on specific customer needs and cases. So at the end of this, we're going to be requesting some feedback on how this has gone. We're going to start off day 2 with sort of a question and answer session. So if you have some questions from the first day's session, or from using the tools in the interim time, this would be a good time. One thing I want to just put up here, and I think we're going to share something that one participant asked that I think is very important to keep in mind as you're doing this modeling. So a lot of what we're doing right now is focusing on the how to use the software, and then how to read the reports and interpret what's going on and what the software is telling you. So there was a really good question about true versus apparent, which I think is worth going over again, because this is very different to what you might be used to in a normal or a non-electrolyte process simulator. So when you're doing modeling electrolyte systems, there's a lot to keep in mind, because there's a lot more happening than just phase changes. And so I think with that, I'm going to pass it back over to Diana for sharing. But if you have questions after she talks a little bit about the recap of last time and this true versus apparent, either raise your hand or just unmute yourself and speak out, and we'll get started that way. So I'm going to stop sharing here.
Thank you, Jordan. Okay, let's see. Could you please let me know if you can see my screen?
Yeah, it looks good.
Okay, I'm using the web app today, not the app, and I don't know how different it is. I just don't see that it's selecting the screen. So thank you. Good morning, everyone. Yes, so thank you for being here today. This is our second day. We are going to increase the pace of the training a little bit more. The first day was just to get familiar, how to use the software, where to find the specific tools, how to add streams, blocks, etc. And today we will just cover more cases and learn other capabilities that the software offers for you to simulate your processes. So as Jordan was mentioning, there was a question regarding the difference between true and apparent species. So I have put this some slides here together just to try to explain the difference, right? So in the reports, what I am showing here is actually very similar to what we have seen in Flowsheet. To the left, I am showing inputs. So we have the conditions and we have the inflows here. So in this case, I have water and sodium chloride. So overall, I want to see what the reports are giving me, right? Like I want to see what's the difference between true and apparent moles. So the definition for true moles is that this is the fully speciated solution. So when you put salt in your water in a beaker, so then this solution is going to dissociate. This sodium chloride is going to dissociate into sodium ions and chloride ions. The apparent moles definition is going to be an apparent representation of the fully speciated solution. So let me explain. So again, you have your water in your beaker. You add 1 mole of sodium chloride of this salt in water, and it's going to fully dissociate. So this is the species output true species. And let me just put this pointer here. The species output true species. True species means the fully speciated solution. So you notice here you have your water, molecular water, 55.5082 moles, equivalent to 1 kilogram of water. And now you're going to have 1 mole of sodium plus 1 mole of chloride minus 1. You also have the dissociation of water, OH minus 1, H plus, and the formation of a little teeny tiny bit of this chlorhydric acid, okay? Because of course you are also dissociating some of these chlorides, but it's minimum. You'll see that it's virtually zero. So this is a fully dissociation of this sodium chloride solution. Now in the report, you will also see something that is called the molecular output, okay? So what the software is going to do is going to attempt to put this fully dissociated solution, all of these species, back into a molecular form, okay? Because it's just easier to manage it that way, okay? You don't want this, these are a lot of species, these are 2, 4, 6 different species, so the software is trying to put all of these species back into molecules so that everything is electrically neutral and is easier to manage, especially if you're working in a process simulator. So then you want to track the total amount of sodium chloride. So what the software is saying, okay, whatever is a molecule, mostly, whatever is a molecule stays as a molecule. Okay, so this water is going to stay as a molecule. But for example, the sodium chloride, now the software is going to put the sodium plus and the chloride plus into this salt, sodium chloride again, and you will also see the formation, or there is a little bit of chlorhydric acid. This molecular output not necessarily matches your original inflow. You see that it's slightly different. In here now is taking into account the formation of chlorhydric acid. And again, this could be probably because we want to maintain electron neutrality. I really don't know the underlying reason why we are forming this tiny amount of chlorhydric acid, but it is there probably because maybe we want to maintain electron neutrality. Or maybe just the dissociation, the initial dissociation, so it wants to keep this chlorhydric acid that you had in your true species up here, down here in this molecular output. So that's the difference. So it's the fully speciated, and then this fully speciated solution then is represented into molecules down here in the molecular output. Okay, so it is called a parent species because it really doesn't represent fully the original input that you enter in the software. Okay, any questions about this? I don't have the chat. I wonder if Sik is here and maybe he can help me. If there are questions, just let me know.
Yeah, I'm checking the chat. I don't see any questions.
Okay, thank you.
Diana, I have one question. Can you hear me?
Yes. Hi, Yin.
Yes, this is Yin. Yeah, hi, good morning. I noticed that these two tables, the true species and apparent species, they have different HCl concentration as a molecule. Is that for the two tables, they are coming from two calculations rather than from one?
They are the same calculation. They are, I put this in the software and they are exactly the same calculation. If you notice, probably it could be, I also wonder that different, I wonder why we are seeing the difference between the chlorhydric acid in the apparent and in the species output. And I just need to find out why we're seeing that slight difference. But they come from the same calculation.
Yeah, and especially in the true species, the HCl as molecule is 10 to the power negative 14. It's higher concentration than in the apparent species. Considering that in the apparent, it must have, the HCl in the true must have added the Ci with some H proton, possibly more will be added, I would think. So this is a little bit problem to me. But this is minor. Sorry, you can answer later.
Oh, no, yeah, no problem. I will also answer your question, Yang, that you had about the H2S. So in this case, this is another example where I am having not only sodium chloride solution, but I'm also having a vapor phase, H2S, and I am having an organic phase, which is decane. Okay, so I am adding 4 different phases here, and this is my original input, and this is the species output. Okay, so I am having the species, the dissociation of H2S. Some of it dissociates into bisulfite, some of it dissociates into the S-2. Okay,
Right.
and we also have the dissociation of sodium chloride here, and so then you'll have the sodium plus the chloride minus, and also the dissociation of water. Okay, so you see all of this dissociation. This is how it dissociates, the total dissociation, and how it distributes in every single one of the phases. So if you are tracking your molecular H2S, you would need to go to your true species table and look for the H2S, that is molecular H2S. Everything else, the other S-2 will be as bisulfide and this S-2 ion, right?
Okay.
Now the software is going to put all of these ions into an apparent report, right? In molecule. So again, this molecular output is not going to match your original inflows, because now this is trying to match the dissociation that you are simulating, okay, or the dissociation that we have in that true species. So what the software is going to do is going to put all the S-2 molecules in this molecular H2S here, but it doesn't mean that this is molecular H2S. Is that it's just putting all the S-2 species into the molecule, but this is apparent. This doesn't mean that it's 100% the molecular H2S. We knew from the true species that it was 0.9994, right?
Yeah.
So in this molecular output, we are simply making a molecular representation of all of the S-2 species.
Okay.
There is a third output that we call the materials balance group output, that we also call the elements balance. And if you are interested to track only the S-2 species, so then I would recommend using this element balance report, because in here you will see how the S-2 distributes in every single one of the phases, independent if it's H2S, bisulfide, or the sulfur -2. Okay? So you can track it just by using this material balance group table. So you have those 3 options. The software provides these 3 options for you to track your specific oxidation state or specific species that you're interested in. Again, the molecular output is just going to find a combination of molecules that summarizes all the dissociation that you have in your true species.
Okay.
And that's it. I hope that answers your question.
Yeah, thank you.
Cool. Okay. So I also hope that this is useful for all of you, so that whenever you go to the report and you see your true species, molecular species, and your materials balance group, you can have a better understanding of how to interpret the results. So if you have any more questions or any not concerns, but you have your curiosity is saying, how do I calculate this, or where do I find specific calculations in the software, either in Flowsheet, Studio, you can always go to the wiki. Oh, I forgot to put it here. But we also have the wiki where you can go and type all your information and all your questions there. Let me just show you the website. We have the wiki of OLI systems, this one, wiki OLI, and in here you can always search for example, true species versus apparent species, and we most of the time have created answers for those typical questions that we receive. So you can go to the wiki, or you can always create an account in the portal. So we have something that is called now the OLI portal. You can create your account, your password, and then in there you can also submit questions, and then you will also find manuals, instructions, etc. Everything in this portal. Okay. So I just adding the LinkedIn page. You will also, if you go to the OLI simulation group, in there you can also ask and post your questions, and then we will also answer to those questions that you post there. Okay, so let's move to our class. I hope that was useful for you. And now we're going to start. We're going to learn how to set up columns in OLI Flowsheet ESP. So what we're going to do is that we're going to start a new simulation. We are going to simulate a simple absorption column. And in the software, you will see that there are two types of multi-stage columns. You will see that there is one that is called an absorber and a stripper. And the most simple of those two is going to be the absorber column. And this column consists, the one that I'm using here is an absorber, and we are going to simulate this. And what we are going to do is that we are going to have a combustion gas, okay, that is coming into this absorber. And this combustion gas will contain all of these inflows here, all of these pollutants. You will have SO2, SO3, chlorhydric acid, some CO2, H2S as well if you want to include it, and mercury as well if you want to include it. I am going to use this chemistry that is more simplified so that the simulations run faster, but you can always add some other pollutants as if you prefer. And what we're going to do is that we are going to use a caustic stream to wash this combustion gas and create a clean gas. Okay. Okay. So let's go to the software. Please open a new file, and let's start creating this simulation. Okay. So the first step for this simulation is to set up the units. But for this simulation, I am going to leave the default units, metric, flow in moles. I'm not going to make any changes. The second step is now to create the chemistry model. Okay, so to do that, we have two options. We can either go to chemistry model here to the left or to the tab. So click on this tab, chemistry tab, and I am going to use the default framework. We're going to leave the AQ framework or the aqueous framework. And once we select the thermodynamic framework that we want to use, then we go to the next tab, which is the inflows tab. Okay, so click on this inflows tab. And in here, we are going to start defining our chemistry. So let's start adding the chemistry. It's going to be nitrogen, N2, CO2. Let me just bring my here, CO2, then goes oxygen, argon, Ar, SO2, SO3, so sulfur dioxide, and we have SO3, and we have two more, chlorhydric acid, HCl, and sodium hydroxide. So we have 2, 4, 6, 8 different components, and of course water goes by default. Yeah, perfect. So now that we have defined our chemistry, now we can go to start building the process. So that's what we're going to do. But one thing, let me just show you one thing here. If you want to change the name of this chemistry, it usually by default is going to change to have it as chemistry, but maybe you will have different chemistry models. So you can always rename this chemistry here, just to differentiate between one chemistry model and the other one. And you can right click on it, and let's name this chemistry model as combustion gas. we'll see that that chemistry model has been changed to combustion gas. You can always add another chemistry model if you want to. I don't know, maybe you want to add a different species, or you want to add, let's say, NOx that we have not included here. And to add a chemistry model, another chemistry model, you can simply go to chemistry and select the option add new chemistry model. But we are going to do only one chemistry model. I'm just showing you here the options of how to add more chemistry models for your simulation. So now we are ready to go to the flow sheet and click on this flow sheet tab to start building the process. Okay, so the first thing is that we are going to add our block. So we are going to go to our library here to the left, okay? And let's look for the absorber. And you will see here that there are two different or similar icons here. One is for the absorber and the other one is for the stripper. The difference between these two is that the absorber by default doesn't bring the reboiler and condenser attached to it, while the stripper will bring a reboiler and condenser attached to it. If you want to add a reboiler or a condenser to the absorber, the option is there, but it just by default doesn't bring them with it. So let's click on this absorber and just drag it into your flow sheet. Okay. And let's rename this absorber. Let's double click on the name and let's rename it gas scrubber. Perfect. So once we have renamed it, I like to usually put this name in the block, not outside, so that we know that it belongs to this block. Okay. Now, make sure, just click on it and make sure that you have selected the absorber, so it's a gas scrubber absorber.
Diana, could we look at the composition of the chemistry again?
Sure, combustion gas. Did I go too fast in that part? Let me see.
No, just we have one user that was having issues entering argon, and just wanted to see how you had entered it.
Yes, okay. Yeah, I entered as AR, but you can also type argon, and the software should have recognized the component argon.
Excellent, thank you.
Thank you. Okay. Perfect. So I will leave this for 10 more seconds, and so that the person that needs to see the chemistry can take a look at it. Okay. So I'm going to go back to the flow sheet, and we will see here that in the errors, we have several warnings, right? In the errors tab, we have several warnings. It says that we need to define a lot of things for the scrubber. And that's correct. For when we are working with a scrubber, the first thing that we need to specify is the calculation method, okay? And to the right in the properties tab or in the properties window here, the first thing that the software is actually highlighting is, please, what is the calculation method? Tell me what is the calculation method. And if you click in this drop-down arrow, you will see that there are two options. So you have the equilibrium option and the mass transfer limited option. We are going to select the equilibrium option. So click on the equilibrium. And this will instruct the software that at each column, at each one of the column stages, each stage will be calculated at equilibrium, and mass transfer limitations will not be included. But if you include, if you select the option mass transfer, then you will need to define a lot of specifics for the mass transfer limitation. So let me show you. So if you select mass transfer limited, So down here, there will be under parameters, there will be a lot of information that the software will be asking you. Is this a packed column? Is this a safe column, a bubble cap, a valve tray? And you will need to define the stage height, all of this information for the mass transfer column. For our example, we are going to leave it in at equilibrium. So everything, so the software will basically say at each stage, everything reaches equilibrium, okay? The next step is to define the number of stages for this specific example. By default, the software says it's 10, but we are going to simulate this observer using 3 different stages. So enter 3, overwrite that 10 with a 3. And this will instruct the software that there will be 3 theoretical stages in the column, okay? We are not going to include a condenser, and we are not going to include a reboiler, so we will leave the defaults no. The next important piece of information here that we need to define, and you will see also in the error messages down here, is that we need to specify the column pressure. So we need to go to the parameters section, okay, and we will explore some of the other options here, but we are going to start first with the pressure profile, the third option here in the parameter section. So go to pressure profile and click on this gray button down here. That will take you to a new window or a new section of this properties panel. And in here, we are going to define the pressure profile within the column. So the stage 3, which is the top stage, will have a pressure of 1 atmosphere. We will enter 1. And the stage at the bottom, which is stage 1, will be will have a pressure of 1 atmosphere. Okay. So what we are saying here is that there is not a pressure drop across the column. Okay. So what the software is going to do is going to, let's say we had 10 different stages here. So all the 8 different stages will be interpolated between these 2 numbers, and then what the software is going to assume is that everything else is going to have a pressure of 1. So in this case, we have 3 stages, and this is stage 2. The number of that stage 2 for the pressure will be interpolated between 1 and 1, meaning that here the software will assume that the pressure is 1. Okay, so you don't need to enter that. If you prefer, you could enter it, but there is no need because the software will calculate that for you. Okay, so the warnings, the error messages down here, we still have some errors, and it's because we need to specify the inlets and the outlet streams. So we're going to start adding or connecting some streams here. So we are going to go here in the toolbars, and we are going to select the Add a Stream button. So we're going to start connecting here. First, the inlets. So the first inlet that we had, that I showed at the beginning, was the combustion gas. And that combustion gas is going to come from the bottom of this gas scrubber. So we're going to click on this white area and then make sure that we see the feed at the stage 1. That is the tag that you should see. Feed stage 1. Click on the arrow and then you make the connection. Then the second stream is going to be the caustic, the one that we're going to use to wash that combustion gas. So we click on the white area and then move to find the feed stage 3, which is the top stage, and make that connection. So we have the caustic, combustion gas, and now we need to create the outlet streams. We will have our clean gas, that is the vapor outlet, the one at the top here. So we will have the vapor outlet. So we click on this arrow, and then I'm going to make a diagonal so it goes. Oops, it didn't do what I wanted. So I'm going to delete it. Well, it's okay. Let's leave it like that. And then is going to, the next one is we are going to define the buttons for this absorber. Again, go to the bottom here. It's going to be our liquid outlet. So just click on that arrow, and it goes like that. Okay, perfect. So we have created here the gas scrubber. We need to rename these streams. I'm going to click my selector here to start changing names. So let's start with this name up here. This one is caustic. And down here we have our combustion gas. Okay, this will be my clean gas. Put that here. And finally, we have, for this one at the bottom, we say that it's bottoms. Perfect. At this point, let's go ahead and save this file just in case. So go to File, Save As, and I am going to save this case for these class files here, and I am going to save it as a basic scrubber. Okay. So let's click on Save. Now my file has been renamed, and we can go ahead and continue with the simulation. So now what we need to do is to define the stream compositions, okay? So let me bring here the presentation. So the software, for the simulation, we are going to say that the combustion gas, the total flow, it has been defined in cubic meters per hour, and the inflows, you'll see that they come in mole percent, okay? For the caustic stream, it's different. The total flow is in liters per hour, and the inflows is defined in mass percent. So we need to play with this. Now, probably our units that we initially defined are not going to help us with this. So we need to change our units for the combustion gas and for the caustic. The reason why we're going to do it, the reason why I didn't set up the units at the beginning for the combustion gas and the caustic is because I want to show you another way as you go in the simulation how to change your units. So click on this combustion gas, okay, and to the right you will see your properties panel. So we know that the total flow needs to be cubic meters per hour, and the inflows need to be mole percent. So click on any of these hyperlinks, maybe the one on inflows, moles per hour. Click on that. That should immediately bring your units manager. And in here we are going to modify the units before adding any information in the properties panel. So the total flow is not going to be in moles. We are going to define it in volume. Okay, so this total flow, you'll see that moles, if you click on it, there is a drop down arrow. We're going to click on that. And there are three options. We have mass, moles, and volume. Click on volume. And you'll see that the software is saying, based on the original units, that volume will be in liters per hour. I will change this later. Let's continue with the next one, which is the inflows. With the inflows, those inflows were given to us in mole fraction. So we are going to click in moles, click on the drop-down arrow, and look for the option mole fraction. Okay? And the default unit is mole percent. This is the unit that I want, so I don't need to change this unit. There is another output variable that I would like to change. That will be the vapor composition. So for this one, again, I want to define it in mole fraction. Click mole fraction. And then you will have You also have that the units is in mole percent. We are happy with that. But now I want to change this liters per hour. I don't want it, I want it on in cubic meters, okay? So how do I do that? Like you see that in here, this is yellow. That means I cannot edit it. So you go down here where it says basis options for volume. And for that specific volume, now you can change how you want to report that volume. By default, liters per hour, but you can click in this drop-down arrow and look for any of the options that we have here. I want cubic meters per hour, so I select cubic meters per hour. I made a change here, and it immediately changes up here for the total flow. Okay, so 3 changes I made: the total flow, volume, cubic meters per hour, inflows, mole fraction in mole percent, vapor composition, mole fraction, mole percent, and that's all what I'm going to do. Then to accept the changes, I click OK. And please notice your properties panel. Now it has changed the units to the specific units that I want. So now we are going to enter the conditions for this combustion gas. So the conditions for this combustion gas is going to be temperature 100 degrees C, pressure 1 atmosphere, so we're good with that. The total flow is going to be 100 cubic meters per hour. Okay, now we need to enter the inflows for this gas, for this combustion gas. So we have that the water amount is going to be 8%, nitrogen is going to be 73%, CO2 is 11%, oxygen 6%, argon 0.8%, sulfur dioxide or SO2 0.2%. Then we have SO3 0.01%, sulfuric acid 0.005 or 5 to the minus 3. Okay, now you'll see that there is a red. The total here is in red because it doesn't quite add up to 100%. Okay, so you can either play with maybe the concentration of oxygen here until you reach your 100%, or you can always use what we call a normalization option. So let's say you want to normalize all of these inflows so that they go to 100%. You could normalize these fractions using proration, or you could use them. You could normalize them using makeup with water. So I'm going to select that option. I'm going to instruct the software that not to normalize this 100% or these fractions to 100% by modifying the amount of or the concentration of water. So when I instructed the software to do that, you'll see that the concentration of or the mole percent of water went from 8 to 8.985 mole percent. So you have those two options. You have the proration option or the makeup with water. In this case, I'm using the makeup with water option. Okay, so everything else, advanced options, all of these, we are good. We don't need to turn any of these on or change them. Let's save this. And now we are going to define the caustic stream. That's our other input that we need to define. So if we go back to the presentation again, the total flow, liters per hour, inflows in mass percent. So we need to change those inflows as well, or the units for those inflows as well. So we go to the properties panel for the caustic stream, and we are going to click on the inflows in this hyperlink again, and we are going to open the units manager. Okay, and we are going to do the following, we're going to make the following changes. So total flow, again, is going to be in volume. So we go to moles, click on it, select volume. And I do want the liters per hour. Okay. For inflows, I want mass fraction. I don't want moles. So click on moles and select the option mass fraction. That will be mass percent. I want those units. And I also want to change the aqueous composition to mass fraction. And go to mass fraction. And there it goes. So we made 3 changes: total flow in volume, liters per hour, inflows, mass fraction in mass percent. For the output variables, we changed the aqueous composition to mass fraction in mass percent. There are no changes in these basis options. And then once we are done specifying the units, we click OK. And now we have the changes in my properties panel. And now I can start entering my conditions for this caustic stream. So the temperature for this caustic stream is 25 degrees C. The pressure is 1 atmosphere. And the total flow is 100 liters per hour. Perfect. Just bring my... Okay. The inflows for this caustic stream is relatively simple. We are working with a 10% sodium hydroxide solution in mass percent. So we simply put 10 here. And the rest is going to be water. So we can again, either put 90 here, or we can just simply click on this normalization and then say make up with water. The software will immediately calculate that that is 90%. That's good. 90 here, sodium hydroxide, 10%. Okay, so that means that if you go to your errors tab or errors window here, all the errors are gone, there are no warnings, and that means that we have specified all the basic requirements for this absorber. We can go ahead and save. And please run the simulation. Click on the run button, and then let's analyze the results. So everything went well. You'll see that I have simulation complete. Okay. And then we can understand, or we can go and see how much of the SO2 that was added in this combustion gas was removed, and how much then I have left over in my clean gas. So click on the clean gas stream, okay? And now let's go to you'll see that immediately the properties panel opens in the calculated tab, because this is a calculated stream. And in here, you will see the results for this clean gas. You have 2 different sections, the stream parameters and the total apparent. And for the volume, you have liters per hour. That's 90,000 liters per hour. And you also have that the total apparent molecular composition is in moles per hour. But if you remember, we made all of these changes for the combustion gas. We said the volume is going to be in cubic meters per hour, and the inflows is going to be mole percent. The initial SO2 was 0.2%, so we want to know how much we decrease that, right? But it's difficult to tell in moles per hour. So once again, we need to do, and I promise this is the last time we'll do this. We need to change the units for this clean gas, okay? So that we can compare apples to apples. So click on this clean gas and go to any hyperlink, but let's click on this total apparent molecular hyperlink to open the units manager. And again, we are going to change the total flow to volume. The basis, we need to change it because we don't want it in liters per hour. We are going to change the units for inflows to mole fraction, volume. This is inflows, mole fraction, mole percent. And finally, for the vapor composition, we are going to change it to mole fraction, and it's going to be mole percent. Again, for bases, we need to change this volume down here. For the basis options, we need to change this volume to cubic meters per hour. So it changes up here. And I have one more change here, and it's the total composition for the outputs variable. I also want a mole fraction. So select mole fraction. So I made a total of 5 changes. So I changed the total flow to volume, the inflows to mole fraction, the vapor composition to mole fraction, the total composition to mole fraction, and the volume here in basis options to cubic meters per hour. Those 5 changes. Okay. So click OK. And now we should see our output with the units that we like in order to compare. So for clean gas, the vent temperature is going to be 57.5 degrees C. So remember, this combustion gas had an initial temperature of 100. Now the clean gas is living at 57.5. We initially put in this combustion gas 100 cubic meters per hour, and the clean gas amount or volume that is leaving is 90.2 cubic meters per hour. What about the SO2 and SO3? So you'll see that the combustion gas, we had 0.2 mole percent of SO2, and the SO3 was 0.01. If you go to the clean gas, now you'll see that SO2 is 7.45 10 to the minus 24. This is virtually 0. And SO3 is even smaller than that. Okay? So basically, this SO2 and SO3 are virtually all removed from the combustion gas. Okay? And this is probably due to, in part, because we have added an excess amount of sodium hydroxide. So, for example, you can confirm that you have an excess amount of this caustic stream if you click on these bottoms, the stream down here, click on it, and check the pH. The pH is 8.72, that's almost 9. Okay, so if you see that this pH is basically, this pH is so high that it's a basic pH, right? So what is happening here is that, yes, we are adding too much caustic. It's good from one point of view because we're removing the SO2 and SO3, but it's bad because when we have this high of a pH, it can start causing fouling issues, right? Like in my stages and in my pipes, then I will start forming some solids that eventually will foul and clog the stages and my pipes. So the reason why we may be forming a solid, and let's say probably we're forming a sodium bicarbonate solid, is because this caustic stream, has sodium hydroxide and is going to react with the CO2 that you have in this combustion gas. And that is going to form a solid that is going to be sodium bicarbonate or some type of carbonate. And then that will cause the fouling of your equipment. So can we check if we are actually forming a solid in our stages and in the bottoms of this column? Yes, we can do that. So what we're going to do, or what I'm going to do here, is I'm going to right click on that in this gas scrubber, and I am going to ask the software to add a callout. Okay, you can also add callouts for the units. So in this callout, this is the default values that you will see for the callouts, but I don't want those values. I'm not interested to know that type of information. So what I'm going to do is double click on this, and we are going to delete this just by double clicking on the selected variables. And what I'm going to do is to plot, or not to plot, but just to add here the information regarding scaling tendencies. I want to know if I am fouling my stages, okay? Because maybe that high of a pH is really causing issues. So how do I do that? So you'll see first here that there are two different categories. You can select for general properties or for properties at each stage. I want to select the properties at each stage, and I want that the software shows me the scaling tendencies. So I am going to plot for this specific example the formation of sodium bicarbonate, the one down here, and I am going to put it to the right selected variables. And that's for the bottom stage, that is stage 1. Now select stage 2. Going to do the same selection, sodium bicarbonate. And then the next one is stage 3. And I'm going to select sodium bicarbonate. In reality, we know that the stage 3 is the top column and stage 1 is the bottom. So I'm going to move this up. So select the stage 3, move it up, and select stage 2, move it up. So you have 3, 2, 1. Okay. So we are trying to see if we are forming this solid in our stages. Okay. Now click OK, and I hope that you already have all of this information. We went to scaling tendencies and selected for each one of the stages the formation of this solid nacolite sodium bicarbonate. Okay, so we click OK, and in here you'll see that these are the values for the scaling tendencies. Any value that is below 1 means that the solid is not forming, and any value that is above 1, the scaling tendency above 1, means that the solid is forming. So we have that sodium bicarbonate is being formed at stage 2 and at stage 1. Okay, so we are having a fouling issue that in the stage 2 and stage 1 of this column. Okay, so this is a problem, and that means that we need to solve it. But how do we do this? How are we going to make sure that we are not fouling my column, while at the same time I want to make sure that I am not releasing SO2 or SO3 to the environment? Okay, so what we are going to do, and I'm going to give a break after this, and what we're going to do in our next example is that we're going to learn how to use the specification and control option for this gas scrubber, so that we can make sure that we follow or we release a certain amount or some specifications for this SO2 and SO3 to the environment. But I also want that the software calculates the optimal amount of caustic that I need to reach that specification, while at the same time I don't have any fouling in my column. Okay, so I'm going to give 6 minutes for a break. So please go ahead for some coffee, and then when we come back, then we will continue on this example. I'm going to save it. So we will meet in 6 minutes. You know what? I didn't put my timer.
Hey, Diana,
Sure.
click on the caustic stream. So just to see the composition and how it's set up.
Yeah.
We're having one of the, I think, having an error getting ionic strength of the aqueous phase is too large, whereas 42.3 results may be an error. So I was wondering if you could leave that up and we can take a look.
So what is the question?
Question is that the user is getting an error message when trying to run the column.
Oh.
On the ionic strength of the aqueous phase.
Okay. yeah, I will leave it there, and we will meet at the top of the hour, and then we can see what could be causing that error message.
Okay, thank you.
Okay, I'm back. I see questions here, Azuma. Okay, let me see.
Yeah, that's the question on the error message. Asuma now is checking the chemistry model, make sure he's got AQ selected.
Yeah.
He said his caustic stream is the same. I'm assuming the combustion gas stream should be the same.
Yes, so to check, let me see, the question is, where can I check that the AQ model is set? So we need to go to the chemistry model for the combustion gas here in this tab. And if you go and click on data banks, you should see the AQ framework, the aqueous framework selected. That is where you check that. The other problem could be that, yeah, the caustic stream needs to be, we need to make sure that we have the total flow in liters per hour. And our mass percent for inflows is 10%, 10 weight percent of sodium hydroxide and 90% for water. So Uzuma, if you could let us know if you...
Yeah, and he did say that he had that. And his stream is set in mass percent.
Yeah,
he's got
just to avoid the back and forth chats. So yeah, the caustic is set 25 degrees C, 1 atmosphere, 100 liter per hour. It's a 90-10 by mass, H2O to NaOH. That's my caustic. Combustion gas is set 100 degrees C, 100 meter cube or cubic meter per hour. And then the same makeup, the difference is made up by water. With regards to the AQ, that's the only part that I'm not 100% sure.
Yeah,
So I go,
yeah, if you go here to your combustion gas data bank, it should say AQ.
in the chemistry tab, yeah.
Yeah, the chemistry.
And it says thermodynamic framework is aqueous.
Yeah, so that's how you know that it's using the AQ framework.
Mm-hmm. Yeah, it's that's the same thing I have set up.
That is very weird. Do you think you could share really quickly your screen and see what could be?
Sure.
Just to identify that what could be causing that.
Let me know when you can see it. All right. So starting from top.
Still loading. Okay.
Yeah, all right. This is a combustion gas.
Could you please, why do we have all of those data banks? We should only have the AQ.
Yeah, they're not added though.
They are.
Are they?
Yeah. So click on them and
they're not added.
click on only one of them and see ion exchange, for example.
Okay.
Remove. Surface complexation, remove. Geochemical, remove. Yeah. Just leave only the AQ framework. We are not using any of those special data banks. Okay, let's go back to the flow sheet.
So we run it again? Or you want to check?
Go ahead and run it and see.
Yeah, that will take care of it. All right. Yeah.
Good.
The discrepancies here is gone. Thanks.
No problem. Yeah. And that's a good point. It's a good thing that you shared this with us, just to highlight that again. Whenever we are working with spatial data banks, and let me just, I forget that I have to share my screen again. I think it's screen 2. Please let me know if you see my screen. Zeke, can you see my screen?
Yes, ma'am.
Great, thank you. So every time that I know that we have this option here of add all of these data banks. but only when we are sure that we need them for our calculations, then we can add them. But I wouldn't usually recommend that because it can cause issues. For example, the ionic or the surface complexation data bank is specifically when we are dealing with surface complexation reactions. So we don't need it. And when we start adding all of these options in our data banks, then it makes our calculations more complicated to converge, to run. And usually when you're using a corrosion data bank, you don't need the geochemical, for example, or the ceramics. So you don't need to add them all for your calculations. Only for specific applications is where we make use of these special data banks. Okay. I know that we have something that is called the first, what is the name? The wizard. How do we call it? The first runner. When you install the software, there is an option where you can set up units, you can set up data banks. I think it's the first run.
First run wizard.
The first run wizard. So yeah, I realized that it gives you the option. That first run wizard gives us the option to add all of these data banks, and sometimes that is not a good idea. So I would recommend to double check your settings and make sure that you don't add those special data banks for your simulations, because they just are more expensive in calculation time, and sometimes it just causes issues with your simulations. Thank you for that, Ozuma. That's something very good to highlight. Okay, so let's continue with our simulation. What we are going to do now, and this is just what we did so far, is that we just set up a basic lab absorber, but the absorber has much more than just inlets and outlets. You can also set specifications in this column, and if you click on it, you'll see to the right that you'll see that there are a lot of options, right? You can specify specifications and controls. You also have, if you have reboilers, you can also specify your heat exchanger duties, estimates, tray efficiencies, all of this. So what we're going to learn today is how to set up a specification and control for this column. Okay, so click on this. Let's click on the scrubber. Click on this edit button here. Okay, and that is going to open a new window. Okay, so the idea is, when we left the example, was that we wanted to remove, or we wanted to reach a specific target concentration of SO2 in the clean gas, but at the same time we didn't want to add so much of that sodium hydroxide because we are causing fouling in our column. So according to the literature, and I'm going to bring this presentation here, according to the literature, the target the target limit for SO2 is either 180 nanograms per joule of energy, or a flat 95% reduction. Okay. So our target, so what we're going to use for our simulation is, we're going to say, okay, we are, based on our initial SO2, we are going to reduce 95% of that SO2 that we have in our combustion gas. So as you remember, in our simulation, we had a 0.2 small percent for that SO2. So a 95% reduction will be 0.01 mole percent in our clean gas. Okay, so that's what we are going to enter in our specification window. Okay, so how do we enter a specification? So the first thing is, okay, we went to specs control, click on the edit button here. That opens this new window. And the next step is click on this add button, okay, to add a new specification. So if you click here, you will see that immediately now this specification and control sections are enabled. And now you need to make sure that you set this specification and control sections in the way that you need in order to meet your specifications. Okay, so we are going to start with the specification. So we want our specification variable will be the vapor composition. Okay, because we want to meet a target of SO2 in our vapor composition at the top of my tower. So that will be the stage number. We don't want the stage number 1, which is the bottom. We want to change this to stage number 3. Okay, that is where our clean gas lives. And then we already know that 95% reduction of 0.2% is 0.01 mole percent. So we need to change these units here. We're going to change it to mole percent. And our target value is going to be 0.01. Okay, so that is our specification. Now, what are we going to move within the tower in order to reach this specification? So what we're going to move, or the control variable that we're going to move, is the caustic stream. Okay, so the caustic stream, you know that it comes, so the control variable is going to be a stream. So change this exchanger duty to feed stream flow. Okay, so we're going to move a stream flow that comes in our stage 3. That's the caustic stream, right? If I move this, so that will be this caustic stream that comes here. So select the stage 3 at the top, okay, where the caustic is entering, okay? So again, we are saying 0.01 of SO2. Oh, this is a good point. 0.01 of SO2. We haven't selected the SO2. We have told the software or instructed the software that it's going to be 0.01 mole percent in the vapor composition, but we haven't instructed the software for which component. So once we enter this 0.01 mole percent, you'll see to the right, there is a button that says select component. So click on this select component option. That brings another window where you are going to select the target component that you want to reach. So that will be SO2. So check on SO2, and that's it. We're not going to meet another specification, but only for SO2. So click OK. So again, we have specified this. We have specified that we want a vapor composition of SO2 in the clean gas of 0.01 mole percent by changing the caustic stream in the stage 3 that is entering here. That's all what we have instructed the software. So click OK. And now we're going to save this file, and we are going to save it with a different name because we have made a modification here. So we are going to go to File, Save As, and we are going to name it Basic Scrubber with Spec Control. Specification control or specification or something like that, so you remember that you made that change. Cool. So now we can click Save, and now we are ready to run. Okay, so this simulation, all of you should see that the simulation has failed. Okay, this failure was designed just to show you what happens when you have a failed simulation and how you can troubleshoot this type of simulations. Okay, now, is everyone's simulation failing? I hope so, because if we if we enter the specifications right, we should have seen this failure here. Okay, now, how do we troubleshoot this? We click OK, and what we're going to do, we'll see first the errors here, right? Like I was saying that the block failed to converge, and it's saying that the electrolyte equilibrium error in the column, gas scrubber, and that this will be terminated. Okay, that is a little bit dramatic, but okay, we go to the output tray, the output tab down here. I'm going to see what's going on. Okay, so I will scroll up. Okay, so I will see here what's going on. So the software generated the chemistry. Okay, it identified the streams, combustion gas, and combustion and the caustic stream. Okay, it started to do the simulation in the gas scrubber here. Start to do. You'll see that there are several values here, and then there is not a number. It seems that everything started to go wrong in the third iteration. Then again, it tried to do another iteration, but it just failed. What about, let me see, if you go down for the stream 1, so for the stream 1, combustion gas, it calculates all the properties for the vapor phase, okay? And then for stream 2, it starts to calculate all the properties for this caustic stream. But I want you to notice something. Let's scroll down here and notice the pH of this solution. The pH of this solution is 14.5. This is a strong indication that we are using a very concentrated or a very basic pH for this simulation. Okay, so what could be happening is that we are telling the software to reach a specific concentration of SO2, but maybe even if you add a little bit of this solution, it is not meeting this specification here. Okay, so it's likely that the software cannot find a caustic float rate that sets that vapor to 0.01%. If you remember in the original simulation, we had that vapor percent was like it was 10 to the minus 25 or something. So that means that yes, this caustic stream is really concentrated, and even if you add a little bit, it's not reaching that specification. Additionally, if you are adding a little bit of that caustic stream, it comes in a liquid phase. But maybe it's too hot, you're adding a little bit of that mass here, and everything is becoming into a vapor phase. And if you have everything a vapor here, this simulation will fail. You need a liquid and a vapor phase so that the vapor equilibrium equations can be solved. So that could be possibly the problem. So what we are going to do is we're going to dilute this caustic stream and see if the error can be solved. So click on this caustic stream here, and now let's change this mass percent of sodium hydroxide to, I don't know, let's do 0.5 mass percent. Okay. We already used the makeup with water, so now the water immediately changes to 99.5%. Okay. Save the file and let's run it again and see if now our simulation converges. Perfect. Okay, now it did. So in fact, we did have a very concentrated caustic solution that was this caustic solution was having a problem trying to get this clean gas to 0.01% mole percent. Okay. So let's analyze the results. Let's select this clean gas and go to the total apparent molecular and check for SO2. So you'll see that the target SO2 is 0.01 per design. So it is doing what it's supposed to do here. Okay. And how much caustic did it need? So click on the caustic. We are going to go to the, we initially put 100 liters per hour, but let's see how many liters actually it needed. So click on this calculated tab. And you'll see here the total volume that it needed was 55 liters or 55.5 liters at 0.5% caustic solution. Okay. So if we would have left the 10% sodium hydroxide solution, probably we would have needed less than these 55 liters. And again, because we are using less than this amount, maybe it would have been, I don't know, maybe 5 liters per hour. The liquid that you enter here will evaporate, and because you don't have a liquid coming into here, so then the stage or the column just fails to converge. Okay, so we accomplished, by diluting this caustic solution, we accomplished our goal of SO2 0.01. What about the fouling? Okay, are we still having fouling issues? So you'll notice that no, down here for the gas scrubber for each one of the stages, the scaling tendencies are all below 1. And that means that now we are not having fouling issues, so we are good. Okay, so the main goal that was to find how much caustic to reach the target specification and to reduce the fouling problems is met. So that is very good. Okay, so one last thing I want to point out before we go to the next example is, how do you interpret this output here? Sometimes it's important to know what the software is doing here when it's doing some calculations, okay? So this is different than a controller. We are going to have different or a different output here for this column. So what we are going to see here is, again, initialization of the process or the chemistry model, the calculation of, or it knows which are the input streams, the combustion gas, the caustic stream. Then it knows what is the block that it needs to solve. And then you will see here a table where it has different pieces of information. So you will have the number of iterations, you have the norm, which is a value for the error, then you have the residual, VLE, etc. So what do they mean? Really, when you're doing all of these simulations, the only value that at the end of the day matters to check is this residual, value here. Okay, so this residual value, you can think of it as the absolute error. Okay, so the closest this value is to 0, the more accurate the simulation is. Okay, then you have the VLE, vapor liquid equilibria. This represents all the error that we have for all the vapor liquid equilibria reactions that we are using in the simulation. We have M balance, that means mass balance, again, represents the error of the overall mass balance in the simulation. H balance is the heat balance or enthalpy balance. That's the error of the overall heat balance. And then you have the last one here is the sum X and sum Y. And that is representing the sum of all the liquid phase mole fractions and all the vapor phase mole fractions. Okay, and again, this is an error that we are counting here, and we want it to be near to 0. Okay, and now how does the software know where to stop? How does it know how many which value does it need to stop to the simulation? This is really set in our convergence tolerance. So whenever you're running this calculation or this specific absorber, if you click on it, you'll see down here in the properties panel, down here there is a convergence option. okay? So if you click on this gray button, you'll see how many maximum iterations are set and the convergence tolerance for the error, right? Like by default, we are saying that it's 5 times to the minus 10. That is going to be, that's the convergence tolerance. And that means that the software is going to stop, especially for the residual value. This is the one that matters. That residual value will stop when it meets that specific convergence tolerance. So we specified it 5, 10 to the minus 7. And when this residual value reaches 10 to the minus 7, or 5, 10 to the minus 7, then the simulation stops. Okay, and it's below the number of iterations that we also have set up for this specific block. Okay, so that is how you interpret this convergence for the column. And you can always play with this, right? You can always increase iterations if your simulation is a little complicated, or play with this convergence tolerance, etc. Okay, so that is how you interpret the output. Yep.
Can we look at the settings just one more time? We're having someone who still can't converge the column.
Oh, sure. The settings for the column?
The column settings and the spec controls.
Yeah, the spec controls. So we have the specification. The spec variable is vapor composition. Stage number is 3. The top one. We need to change the units here for the mole percent, 0.01. Make sure that you click on select components and you select SO2. We need to specifically tell the software that the SO2 is the one that we want to have as a target gas in the clean gas stream. And then after that, we click OK or cancel. In this case, I'll cancel because I don't want to make any changes. We're saying that the variable that we're changing is a caustic stream. Also, the top stage. And then again, cancel. Another thing that maybe we need to check is if we change the, let me see, if we change the sodium hydroxide 0.5 to 0.5% for the inflows. Let me go back to specs control just in case. Okay. I hope that was useful. Let me know.
I've asked Mohammed to let us know if he's converged, or if he continues to have issues, then maybe we can take it offline as well.
Yeah, another thing is he can share the screen so we can see what setting probably is having an issue there. Okay, so now we go to the next.
Converged.
Perfect. That's great. I wonder what it was. Okay, great. Somehow it was not selected. Okay, good. Yeah, the SO2 wasn't selected here. Okay, that's good. Thank you. Perfect. So let's save this. And let's start now with the next topic that is going to be, even though it's a next stop, it's a new topic, we are going to still building up. We're going to use the case that we have so far. And we're going to learn how to set up sensitivity analysis. Okay. For this sensitivity analysis, we are going, let me go back. So what do I want to accomplish with the sensitivity analysis? At first, I want to show you how to set up one of these sensitivity analysis. And the other one is that maybe in our process of this absorber, this combustion gas changes over time. Maybe the composition of my SO2 one day is 0.2%. Tomorrow is 0.8%. there is a bad day and now the SO2 is 2%, you know, like maybe it changes. So we want to understand, or we want to investigate how much of that caustic that we are entering here, or that we are adding to the column, how much of that caustic we need to use depending upon the change of this SO2 content in my gas scrubbers. Okay, so how much of that do I need as this SO2 changes? That's what I want to do. That's what I want to investigate. Okay, so with the sensitivity analysis, we will be able to do that instead of us changing this combustion gas composition manually, right? Instead of changing, okay, 0.4. Now, what is the result? Now, 0.8. What is the result? No, we can do it easily just by using the sensitivity analysis, and you'll see that it's very easy to set up. But I just want you to become familiar where to find things, how to set it up, what does it mean, etc. Okay, so before we continue, let's save this new file, or this file, as, how do we name it? Let's save it as basic scrubber, and we're going to put with sensitivity analysis. Perfect. So I'm going, I got the new name because we are going to make some other changes here. So how do I add a sensitivity analysis? You go to the menu bar and you will find the option that says analysis. And in here, you'll see that there are two different types of analysis. And maybe in the next hour, then we will start doing the other analysis, which is the water analysis. But then for this specific example, we are going to select sensitivity analysis. Okay, so click on sensitivity analysis. Okay. And in here, it will take us to a new window or a new tab. You'll see that there is a new tab that has been added here. So what we're going to do is we're going to go back to the flow sheet because I forgot one step before we add the sensitivity analysis. And is that we are going to add a manipulator in front of this combustion gas because we want to adjust the combustion gas composition for SO2. So let's how do you say this? Let's disconnect this string. We don't want it to go directly to the scrubber. Okay. What we're going to do is we're going to bring a manipulator object from the library. So we go find the manipulator, and we will add it here in front of the combustion gas. We will connect this combustion gas to our manipulator. I'm not going to change the name of the manipulator. It's the only one in this simulation, so there is no point. But let's remember that it's called manipulator 1. Now let's add a new stream. Now we're going to connect. Oops, I didn't select it. We're going to connect this outlet to the bottom of the column, to the stage 1, the feed stage 1. Perfect. And now we're going to rename this adjusted combustion gas. And that's a long name. That's what I want. Let me bring my cheat sheet here. I want to have my case just because maybe I can skip something and I don't want to skip anything here. Okay, there it goes. Okay, so we have adjusted combustion gas, and now we need to set up the manipulator, right? Every time we add a block, we need to make sure that we are setting the block with the requirements we want, or the specifications we want. So we are going to change, we're going to click on the manipulator, and we are going to go to the properties of this manipulator, and we are going to click here, manipulation type. By default is the total flow. But as I explained before, I don't want to change the total flow. I want to change the composition of SO2. Okay, so we're going to change this manipulation type to stream components. Okay, and what this is going to do is it's going to allow me to change the concentration of a specific component in my combustion gas stream. So if you click in the flow factors for that gray area, sorry, I went too fast. Flow factors, click on this gray area here, this gray button. You'll see that now all the components are listed here, and you could change. By default is 1, meaning that all of them are following the same ratio as you enter them. But you could say, I want that now the SO2 is 0.5%, or I want it to be 10 times. This is a multiplier, so it's actually 10 times, or 0. Or half of the SO2, etc. But we are not going to change anything here because with the sensitivity analysis, we will be able to manipulate this directly from the sensitivity analysis. What we do need to specify is that the manipulation type is stream components. Okay? So that is what we needed to do. That's the small change here, add a manipulator, and that's good. Let's save. Then we go to the sensitivity tab. Okay, in there, we are going to instruct the software to change the composition of the composition of the combustion gas, and then we are going to monitor some variables. Okay, so let's start with the parameter section. Okay, so we are going to set up the variable we want to change. So to do that, we're going to click on this add button to the right. Okay, so click on the add button. Immediately says, okay, you have created a new parameter. And what we want to do is to select the block that I am going to use in order to change the composition of the SO2 in my combustion gas. So that block will be my manipulator, the one that I just created. Okay. And what do I want to change specifically from this parameter, from this block parameter, is going to be the SO2 flow factor. Okay. Then what we're going to do is set a value for the where to start the sensitivity analysis and when to end it. Okay, so in here, this starting value is a flow factor, it's a multiplier. So if we put a starting value of 1, that means that we are representing. Let me go back. That means that we are representing this composition of SO2, 0.2 mole percent, because I'm just multiplying it by 1. Okay. So that one value here, the multiplier, is saying that this is exactly 0.2 mole percent of SO2. For the end value, then I am going to say that this concentration will be 10 times the initial concentration. So it will be multiplied by 10, and that will be 2%, 2 mole percent. So we are going to do a survey from 1 up to 10 for the flow factor of SO2, and we are going to plot, maybe let's do this by increments of 1 rather than 10 steps. So we have 1, 10, an increment of 1. That's how we are going to define it here. Okay, so that is with regards to the parameter section. That's what we want to change. Now, what do we want to monitor? What do we want to see? So we go to the monitor variables here. And by default, you'll see that the software is saying, I will calculate all the streams, but for all the streams, I will calculate all the basic parameters. Okay, so if you are happy with this selection, basic parameters mean temperature, pressure, and some properties such as pH. It will also calculate the total volume, the total mass, and the total moles. If you want to know specifically the composition of SO2, or if you want to know the a thermodynamic property, you would need to specify it here. The software will not provide that to you. You need to make sure to tell the software, to ask the software to calculate that property for you. Okay? So what I want the software to give me is, I know that I set up the multiplier, but I want to know specifically the concentration, or I want to know the actual moles or the mole percent of SO2 that is being changed as I go through the sensitivity analysis. So I will ask the software to monitor or to track the SO2. So I will add a new monitor variable here. So I will just click add. And again, now you have a new variable. And what I want to monitor there is to say, okay, I want to monitor the stream adjusted combustion gas. And the variable type is the composition apparent molecule, the apparent composition of SO2. So I click on select components, okay, and I look for SO2. It's basically the last one here, SO2 and SO3. So click on SO2, okay. So we want to monitor the variable adjusted combustion gas, the composition, the apparent composition of SO2. Then click OK. And now we are all set. That's all what we need to do to set up a sensitivity analysis. Okay, so now what's next? How do I run this? So I just simply go to the calculate button here and run the simulation. Okay, so this is going to take a little bit longer than the original one because it's now going through every single flow factor of SO2, okay, and it's going to calculate every single point. And of course, that is going to take a little longer than only one single simulation. So your plot probably is showing you, let me see, it's taking here some time. So your plot probably is showing you in the x-axis, in the y-axis is the moles of SO2. And in the x-axis is showing you the flow factor of SO2, how much you're changing the value of SO2 in the manipulator. Okay. I just got stuck in there. Let me know if your simulation is done. This one is still going. My computer sometimes is a little bit slow. Okay. There it goes. Nice. Okay. Perfect. So this is a default plot. This plot really is not telling me anything. I am not understanding what this is telling me. This is saying that as I, well, actually, yes, it's saying that as I change the amount of SO2 or the flow factor of SO2, these are how many moles I am adding to the system. But that's not what I want. This is not the plot I want to see. What I want to see is how much caustic do I need as I change the composition of SO2 in my combustion gas. Okay, so what we're going to do here is we're going to go to the select data option or here in the upper right corner in the plot. And I don't want to plot this in the y1 axis. I'm going to double click on it to delete it. I don't want it. So we can just simply double click and that's it. So now what I want to do is to go to the stream variables for the adjusted combustion gas. So you see there are two different types of categories, sensitivity parameters and stream variables. And you need in here to tell the software which stream you want to analyze, okay? So for the adjusted, so in here you select adjusted combustion gas, okay? And in here you'll see these are all the basic parameters that were calculated the stream parameters, phase flows. No thermodynamic properties were calculated because we didn't ask for any. And the only thing that was calculated for us was the total apparent molecular of SO2 because that's what we requested specifically. So we are going to go to total apparent and we are going to select this SO2 value here, or this SO2 option here. And we are going to put it, where are we going to put this? We are going to put it in the x-axis. That's the x-axis is how much of SO2 I changed, right? I have changed or I have used, or how much of SO2 I have in my combustion gas. So I use this right arrow here, just click on it. That will overwrite here the previous x-axis that you had by default. So you should see SO2 apparent adjusted combustion gas. And the other thing that I want is to plot the volume of the caustic needed in order to reach the target specification. So we go to stream variables, select caustic, and we go to stream parameters. Oh, I'm sorry, no, stream parameters, no, phase flows. And in phase flows, we are going to select the option volume, the last one here. Okay, so you put it in the y1 axis, and that is what I'm saying. I'm saying as I change the SO2 in the combustion gas, what is the volume of the caustic? Okay, so this is the plot, and here you'll see there is an increase in the volume. As you increase the SO2 in the combustion gas, you need more of this caustic stream. So you started with a very small value, 55.5, and now if you have 2% of SO2, you need 454. This is basically a linear response that you see here. But again, down here, notice that the SO2 is being reported as mole per hour. And we know that we enter this SO2 in mole percent. So we can change these units, okay? So how do you change the units of this plot? You simply go, as you are in this plot tab, you go to the units manager. And what you're going to do here is going to customize, okay? And we are going to go to the output variables and select the option total composition. And we are going to change this to mole fraction. So it changes to mole percent. The only change again is total composition to mole fraction, and that's it. We don't need to change anything else. Then click OK. Click OK.
Hey, Diana, I think we may have had your audio cut out for that last bit on the table. So if you would just walk through that one moment again, that would be great. Just the last bit.
Okay, sorry, I don't know when it cut out, so I apologize.
Oh, okay. No, maybe it's just my end. Sorry, go ahead.
No problem, sure. So, and I am also seeing a question here, how do I change the units of the simulated variable? So, yeah, I'm going to go over that again. So in here, in this x-axis, we had moles per hour. And we didn't want the moles per hour. I want to know the mole percent because we started with 0.2%, right? Now, what happens if I increase it to 0.4%, 0.8%, etc.? So with the mole per hour was really difficult to see that. So while you are in the plot tab, what you're going to do is you go to the units manager here, click on the icon, and you're going to click customize. In order to change the units from moles that I initially had to the mole fraction, I am going to go to the output variables because the plot is going to be only output variables. And I know that is also a total apparent composition. So I'm going to go to the total composition output variable, and I'm going to change it from moles to mole fraction. Okay. Make sure that it's the units you want, mole percent, and after that you just click OK. Okay, then that, and here also you have to click OK, so to accept the changes. And in here you'll see exactly what we wanted to see. As we increase the concentration of SO2 in the adjusted combustion gas, what happens with the volume of caustic that we need in order to reach the target specification of 0.01 mole percent of SO2 in the clean gas. So again, it's a linear response. This is a plot version. If you want to see the data of this plot, you can always click on this show tabular data and just click on it. And you see that to the right, it's going to show you the values of each one of these points. So it says 0.2 mole percent of SO2, that was exactly a flow factor of SO2 of 1. This is the amount of caustic that you need. And as you increase the flow factor to 10, this is the amount of SO2 that you have in your combustion gas. This is how much of the volume for the caustic string you need. Okay, and if you want to export this data, you can always click on this export button up here, and it will create a this is a comma separated value file. That this is basically something that will create an Excel file for you with all of that information. Okay. And regarding the x-axis and y-axis, you'll see here in the properties panel, you can always change the minimums, the maximums, if you want a log scale for your x value, for your x-axis, or if you want a log scale for your y-axis. And you can always play with colors, how you want to represent the plot here, etc. Okay? You have all of these options that you can explore. So this is how you set up a sensitivity analysis. And this is the example I had for that. And I see that now we can go for a short break of 5 minutes, 6 minutes. And then we can come back to do our last example that is going to be a cooling tower example. And in there we will learn how to enter a water analysis and how to set up pumps and heat exchangers. Okay, so I will meet you at the top of the hour. We can start exactly at my 11, and then we can do the last example for the training today. If you have any questions, let me know, and I will mute myself and I'll go for some coffee.
Yeah. Can you leave the scrubber specs on while we're on break?
For the spec control?
I'm assuming so. Maybe QD can tell us what he'd like to see. QD, the main spec. So maybe just leave it like this for now. Okay, I think he's good with that. Okay, thanks, Diana.
No problem. Okay, hello, I'm back. I hope everyone is back too.
Hello, Diana. This is
Hi.
hi. Can you go back? Oh, sorry. I see you have something. Are you going to describe something? Maybe after this, can you go back to the plot and then show a little bit about at the bottom? There's a sliding bar, flow factor. Plot all points. I tried over there. Nothing changed. Is that supposed to be like that?
Oh, this?
Yeah.
Oh, that's a very good question.
What's the purpose of this?
Yeah, I'm trying to figure. Actually, that's a very good question. And I thought that by just changing this, so um, you will select from, let's say, 0.2 to 0.4, and it will reduce your plot from a specific section to another section, but it's not doing it. So probably that is not working correctly. So that's why it selects all points, because it will take
Yeah.
the whole range of your sensitivity analysis. But if you unclick that, so then you can always check from 1 to 3 to 4 to 5 for those specific.
Kind of serving as the kind of blow up or zoom in of the plot, something like that.
Right. Yeah, something like that. But it's not correct. It's not working correctly. So thank you for pointing that out.
Sure. Thank you.
Thank you. Okay. So I don't know if after we finish the sensitivity analysis, I don't know if we saved. Go ahead and save so you have the latest run model here. And now we're going to go to our next example, and let me just bring this here up. And I'm just going to assume everyone is back. So I will just give a few minutes here just to explain what we're going to do, okay? So what we're going to simulate is this cooling tower. This is an open recirculating water system, okay? And we are using an induced draft cooling tower as a cooling unit, okay? And the main components for a cooling tower, so we have our cooling tower, which is the whole orange color here. Then we have a recirculating pump. Then we have a heat exchanger. So how does this work, okay? So what happens is that water from the basin of this cooling tower then is going to go and be pumped to a heat exchanger, where this heat exchanger is going to it's going to pick up, or in this heat exchanger, we are going to pick up all the heat that comes from the process, and now it's going to warm or heat our water. So we need to cool this water, and it's going to be sprayed down this cooling tower, okay? And some air is going to, I don't know what happened. Some air is going to, so the water is going to go down, and some air is going to go up, and that's what is going to do the cooling, okay? Some of that cooling, then you will see that there is some evaporation, okay? So we're losing some water here due to the evaporation that is helping us to cool this water. And because we are losing some of this water, then we need to add some makeup water here to the system due to these evaporation losses, okay? And then everything is going back to the process, right? Everything is going to be recirculated to the heat exchanger, etc. And in some cases, when this concentration here of this water becomes too concentrated, then we need to have a blowdown, just to reduce the concentration of this water here in the basin. And again, well, more makeup water is needed to replace that blowdown stream that we are losing. Right? This is overall how a cooling tower works. And what we're going to do next is to simulate a cooling tower using flowsheet ESP. Okay, so we will be simulating the cooling tower with a separator. Okay, the blow down will be represented by a splitter. The makeup water here will be entered as an ionic input, so we will learn how to enter water analysis. Then this makeup water goes to a pump, and then it goes to the heat exchanger, where then we have heated water that goes back to the cooling tower. And again, the air is going to be represented by this stream here. We will have our evaporate and our blow down. And what we lose in evaporate and blow down will be replenished by this makeup water. Okay, so that's what we're going to do. So let's go to the software. And I am going to open a new file that we are going to start from scratch. Okay, so we will have a new file here. And what is our first step? Our first step is to change the units of our simulation. Okay, so I will not go through the whole changing units in the properties panel. We will do it from the beginning so that we don't have to worry about incompatibilities in the units. So to change the units, we go to the units manager. Okay, we're going to leave it as metric flow moles, but we're going to customize some of these units. So click on the customize button, and we are going to tell the software that the total flow or the total flow rate is going to be given in mass. Okay, so instead of moles, we're going to change the total flow to mass. And I don't want it in grams per hour. This is a big process, so metric tons per hour makes more sense. So we are going to change this to grams per hour. We go to the basis options. We know that is for mass. We look for mass and change this grams per hours. We're going to change it to metric ton per hour. Okay. So again, the only change that we are doing here is total flow, mass, metric ton per hour. We change the mass, the basis option of the mass to metric ton per hour. And that's it. We don't need anything else. We click OK. And again, click OK to accept the changes. So that's all what we needed to do regarding the total flow. Now, the second step after we are happy with the units is we are going to go to our chemistry tab to define our chemistry model. Okay, so we go to chemistry, and so far we have used the AQ framework, but for this example we are going to select the MSC framework. So for thermodynamic framework, let's click on this aqueous framework or this aqueous selection here. And now let's select the second option, which is the MSC. Why am I selecting the MSC and not the AQ model? The reason why I'm selecting the MSC is because at some point in some parts of the process, we may have concentrated solutions, okay? And when we have highly concentrated solutions, the AQ framework doesn't like very much very highly concentrated solutions. The AQ framework sometimes fails when your concentration of water is less than 70% in the stream. So just to be safe, in case we have super highly concentrated solutions, the MSC doesn't have issues with the concentration limit of water. So we are going to work with the MSC. Because of that, that's the reason why, because it just doesn't have issues with concentration limits. Okay, so once we select the MSC framework, make sure that your data bank and the only data bank that you have is the MSC. That is the only one. No special data banks are needed. And then the next step is to go to inflows Okay. And for inflows, we are going to enter the gas components that compose the air, and that's it. So that will be only 4 inflows. We will have CO2. Let me just put it here. CO2. Enter. We also have oxygen. Enter. Argon. And nitrogen. Those are the, oops, yes, this is good that happened. I entered nitrogen, and this always happens to me. I entered nitrogen N2, but notice that the first component that the software selects is this one, this diamino, triazine, something. That's not the one that I want, so I make sure that you select with the mouse, go and select nitrogen N2, okay? Because the other one is not what we need for this simulation. Okay, always double check that you're entering the right inflows for your simulation. Okay, let me just, I always forget to bring my cheat sheet. So let me open my cooling tower here. Okay, so we're done with the inflows. Now you may wonder, okay, you also have some water. You have the makeup water in your simulation. You show that you also have this makeup water analysis here. And yes, that's true, we have that, but we're going to do it in a different way. We're not going to enter in these inflows, we're not going to enter molecular inflows. We are going to enter ionic inflows for that makeup water analysis, okay? So how do we add a water analysis in our chemistry model? So in the menu bar, you will see that there is an option that says analysis. Okay, click on there, and we already went through the sensitivity analysis. Now we are going to go through we're going to select the option add water analysis. And similar to the sensitivity analysis, there is a new tab here named water analysis, okay? And down here you will see, you select the composition option, and the units that are defined for this water analysis are by default milligrams per liter. You can always change these units depending upon how your water analysis was reported. Usually it's milligrams per liter. You will have 2 columns here, 3 columns. You have the component column, the value column, the balance column. We will go through how to use this table in a second, okay? So the water analysis that was given to us for the makeup water was the following. So we have some cations, some anions, some neutrals, and these were the recorded properties. We were given that this was measured at 25 degrees C and 1 atmosphere. The alkalinity is 180 and that the pH is 7. Okay. So what we're going to do is we're going to enter that specific chemistry, okay? So we're going to go here in the value, in the white column where we can edit these values or enter these values, and we're going to enter the following the following water analysis. So we are going to enter that. We're going to say that sodium is 600 milligrams per liter. There is no potassium. Okay, so since there is no potassium and I don't want it here, I'm going to click on the potassium plus 1. I'm going to delete it. So press the delete button and get rid of it. It just should delete that and you shouldn't see it again. So the next one is the calcium plus. Okay, so for that value we have 145 milligrams per liter. The next one is magnesium. That's 100%, 100 milligrams per liter. Then we have strontium. This one here, that will be 0.06. Cool. Now we didn't have any reported value for barium or for iron, so we are going to click on it, on the barium, delete it, and for the Fe2 plus, click on it, and delete it. Sorry. So we have only 4 cations for this water analysis. And now we're going to enter the anions. Okay. So the first anion that I have that was reported was chlorides. So it's 1,280 milligrams per liter. The next one was the sulfate. That's this one, SO4 minus 2. And that's going to be 140. And then I have the bicarbonate ion. Okay. You hover over it, you'll see that it will give you a tag where it tells you the name, the formula, the OLI tag number, and the molecular weight. So this bicarbonate ion was reported to be 180. We don't have bisulfide in this water, delete it. I just don't want to put information that we don't need there, so it just avoids confusion here. And then we have this acetate ion. We also don't have any acetate, so we delete it. We have only 3 anions, chlorides, sulfates, and bicarbonates, and these are the values. And finally, we have some neutrals. So in this water, it was identified that there was some silicon dioxide. Okay, so I'm going to delete the CO2, the H2S. Going to enter the value of silicon dioxide is 30 milligrams per liter. Okay, and there is no boric acid. So again, select it and delete it with the delete key in your keyboard. Okay. Oops, I don't know what I did this. I want just to see the chat window here just in case. Okay. So that we are done with that specification of the composition of this water analysis. And now let me quickly talk about how to interpret what's going on here. You'll see that there is a balanced yellow column where you see that, for example, in this case, sodium plus is being modified to 609. It's not exactly 600, it's not what we entered, but the software is saying that in order for this solution to be electrically neutral or electron neutral, we need to add a little bit more of this sodium plus. Actually, is adding 9.299 milligrams per liter in order to reach electron neutrality. We all know that sometimes there are errors in the measurements of the water analysis, so it doesn't quite match the electron neutrality. So the software is saying that by default is adding sodium plus. Okay, now how does the software know that it has to add sodium plus? So what the software is using is this electron neutrality option that you see here, and it's selecting the balance type dominant ion. So it's noticing that there is more anions than cations, and it's identifying that the sodium is the cation that has the highest concentration. So it is assuming that this is the dominant ion based on these values here, and it will just simply select that dominant ion to increase the concentration of sodium plus to reach electron neutrality. Okay. But there are some other electron neutrality options. You have that the balance type can be prorate cations, prorate anions, and makeup ion. So the prorate cations, if you select it, what it does is that it changes all the cations to keep the same ratio of all the cations in solution, okay? And it just simply modifies all the cations here to reach an electron neutrality. Or you could have selected the prorate anions. So it changes all the anions. In this case, it will reduce the ratio of all of the anions to reach electron neutrality. Or you could select makeup ion, and then you say, I don't want the sodium to be the cation used for electron neutrality. I want it to be the calcium. So the software selects calcium and immediately does the electron neutrality balance for you. Okay? But for this example, we're going to leave it as dominant ion. It's only a 9.2 milligram per liter difference, so we are good. So the next step is, okay, now we need to know the properties of this water analysis, okay? So there are different options, and you'll see that there are 5 different calculation options here. There is a concentration data only, there is a gas phase, measured pH only, and all of these options. I am going to explain only the concentration data only and the measured pH only. And I will provide some information to you of how to understand and use the other options, okay? One thing that I forgot for this water analysis is that in our definition, down here in properties, we need to define the measured properties that were given to us, okay? So in our presentation, it was given the alkalinity and pH, and the software allow us to enter that information, okay? So under definition tab, in the properties section, we're going to enter the measured pH that was a value of 7, and the alkalinity value in milligrams of bicarbonate per liter was 108. Nothing else was given to us. We don't know the density, we don't know the electrical conductivity, none of this. But it's okay, because when we select one of these options, then we can calculate those properties. Okay, so I will select the concentration data only, and what that means is that based on this concentration and this balanced concentration, the software will calculate the properties of the solution. Okay, so to calculate the properties, we go to this button here that says calculate. Okay, we don't go to the run simulation because we don't have any simulation. We want only the properties of this water, so we click on this calculate button. Okay, and it's going to calculate only this water, nothing else. And we go to once it's done, it says simulation completed. It should say water analysis completed. And then we go to the calculated tab in the properties panel. And then you'll see some of the properties were calculated here. You have that the pH is not exactly 7 as it was given in the reported values. It's 7.9. The total dissolved value is 2000. The total dissolved solids TDS is 2300. Alkalinity is almost the same value that was given to us. And if you even want to know more about this water analysis, you simply click on this view detailed report. Okay, so you have all the thermodynamic properties, all the speciation, everything down here. Let's go back to the water analysis. And let's say that the measured pH, you trust this measured pH. It was 7 and you trusted, it was in the laboratory and they said the pH is 7. So when that happens, because it doesn't match, right? Like the pH that the software is calculating is 7.9. That's different. That's almost 8 and it's not 7, the one that was measured in the lab. So when that happens, we're going to select another option that is called the measured pH only. And what that means is that the software will use the concentrations that we enter, and it will also use, you see, I selected the measured pH only, and it will also use some titrants. It will, if you click on the selected titrants, you will see that it will use chlorhydric acid if you need to acidify the solution, or sodium hydroxide if you need to make the solution basic. Okay, so in our case, probably we will be using chlorhydric acid. You can always change this. If you don't want chlorhydric acid, you can use sulfuric acid or nitric acid. You can always change it here. You simply add it in your chemistry tab, and you can select it there from here, from this drop-down arrow. But I'm going to leave the results, and I'm going to go ahead and calculate this water. Okay. And once the simulation is done, then we will go to the calculated tab here to see the pH. So you see that now the pH matches exactly 7. And what the software did is it added chlorhydric acid, almost 16 milligrams per liter. So in there you have to say, okay, which one? What do I do? Do I keep the 7 or do I keep the 7.9? It depends on your judgment of what is the water that really is representing your makeup water for this cooling tower. And again, there are some other options. Those options I will be in here in this slides. I'm providing to you what the software does in every single one of those options. I will not go through that, but just to let you know that those options are here, and you can always play with these options so that you understand how the software thinks and how those options can help you to calculate your properties. Okay, so we're happy with this. We're going to leave the measure pH only stream or the measure pH calculated properties for this simulation. And now we can go ahead and start our simulation. And then I will show you how to bring this water analysis into your process. Okay.
Diana.
Yes, yeah?
Yes, can you please show how did you generate report 2? I missed that part. I do not have report 2.
I go to the calculated tab and I say view detailed report.
Oh, okay, thank you.
Sure, it's just the properties of your water analysis.
And also for the different calculate properties, those slides you just slide through, will you share those slides too?
Yeah, all of what I am showing today will be shared.
Okay, that would be very helpful. Thank you.
No problem. Okay, so let's start building our process. It's going to take us a little while, so no, actually no, it's going to be fine. Let's start with our separator. Okay, so let me show you one last time what we're going to do here. So we're going to say, we're going to build this process, okay? So we're going to start with our separator, which is going to represent our cooling tower. So let's go to our library and click on the separator unit or block and rename this as cooling tower, okay? So the separator will be renamed as cooling tower. Oops. Put the name in the block. Okay, and I'm going to start specifying some streams here. Well, let's click on the cooling tower or in the separator, and let's see what are the specifications for this block. So we will leave it as adiabatic and minimum inlet pressure. Okay, so no changes. Go to the stream to add a stream. Go to stream icon. We're going to enter our air stream here from the bottom to one of the inlets. And then we're going to simulate the evaporate. Okay. So let's change the name for this air. And let's change the name for this evaporate. Okay. So then we will need to add an outlet stream that is going to be a liquid stream, and that will be our cooled water. Okay, that will be cooled. Oops. I don't know, is this how you spell cooled? Now I'm doubting myself. I don't know. But let's imagine it is. Let's assume it is. Okay, so this is evaporate air. Perfect. Now we need to define our inlet streams, okay? I'm not going to put here the reflux stream yet, just because I like to build piece by piece. So let's just start with the specification of this air, okay? So for this air, we're going to have that is going to enter at 21 degrees C. at a pressure of 1 atmosphere, and the total flow is going to be 1,600 metric tons per hour. Okay, that's a lot of air. Actually, I'm checking here my cheat sheet, and it says it's 1,160. So it's 1,160 metric tons per hour. So for the composition of the air, we are going to change this. We need to change these units, the inflow units, to mole percent. So click on the mole per hour and go to inflows and change the units to mole fraction. So that will be mole percent. Then click OK. So now we can enter the fractions here for mole in mole percent. So let's start with CO2. That is going to be 0.041. The oxygen concentration is going to be 20.6. Argon concentration is going to be 0.9. And the nitrogen concentration is going to be 77.2. Okay. We are going to normalize the rest of this composition with water. So we are going to say normalize fractions using makeup with water. And that will be 1.259%. When I was doing this calculation for this composition, I think this was represented at 25% relative humidity in the air, but I'm not entirely positive. But this water here is representing some water content that you have in the air, that you usually don't have dry air in your 100% dry air, right? You have always one composition of water or some composition of water, and that will have an impact in your cooling efficiency, because the more humid the air is, the more difficulty you're going to have for drying or for cooling your water. Okay, so let's save this file. It's time to save. So let's go to File, Save As. And we're going to save this example as cooling tower. Okay, so that will be the name of my file. Now the next block that I am going to add is the one that is going to represent my blow down valve. Okay, so that will be a splitter. So what we're going to do with the splitter, we come here to the library, and I'm going to select the splitter. Put it here in front of the cooled water. And because this is going to represent a valve, I am going to make it smaller. Okay, I don't want it that big. Maybe a little bit small. So it just represents a tiny valve in my process. You go and open or close depending upon what you want, how much blowdown you want. So I'm going to connect this cooled water to my splitter. I am going to change the name of this splitter. I'm going to name it blow down valve. Okay. And a splitter will have minimum 2 outlets. So let's go to the outlet stream, and we will select one outlet at the top and an outlet at the bottom. Okay. We will name the outlet at the top, we will rename it return. This is what we're sending back to the process. And this S2 here, I'm going to rename it blow down. This is what we're getting rid of. Let's put the name here. Okay. Now we need to define this. So what it's saying, you need to define the split specifications of this splitter. So we all know that now we just simply click on the block, and now we are going to define the outlet split here in parameters. So click on the valve, make sure that you are in the properties panel, then click on the outlet split edit button, and that will bring this new table. So For this example, we're going to, the flow bases are going to be in mass. So click on the mass flow bases. And we're going to define the mass fractions. How much of the total amount goes to return? How much of the total amount goes to blow down? So for the return, we're going to send 95% of the total cooled water back to the process, and 0.05 or 5% of the 5% of the total amount of the cool water is going to go as blow down. Okay, that is how we define 95% for return, 0.5 and 5% for blow down. Click OK, and let's save the file. We can go ahead and run just to catch if we have any errors in our simulation. Everything looks fine. The next step is to create the utility tank. Okay, and in here is where we are going to mix the return water with the makeup water. Okay, so that. Yes.
Sorry, I missed your. Which edit did you click? I clicked on the edit, but it's a different window.
Okay.
It's different from here. You have edit split. I have edit component split.
Oh, it's because you selected the wrong splitter.
You selected what?
Probably you selected the component splitter, and we need the splitter. And that's a good point that you brought up. Yeah, I just wanted to highlight that there are differences. The splitter will split total flows, while the component splitter will split specific components from your stream.
Okay, I selected the wrong splitter. Okay, I see.
Maybe only the splitter, component splitter will just allow you to separate components, but no flow.
Okay, I will change that. Thank you.
Sorry about that. I wasn't clear there.
No, it was my fault. Thank you.
Okay, so the next step is to add a mixer. Okay, so we're going to add a mixer. And this mixer is going to receive two things. It's going to receive my makeup water, and it's going to receive my return stream. So this mixer, I don't want it to look like this triangle. I want it to look like a tank. So what I'm going to do is right click on it, and you'll see that there is an option that says icon. Okay. And with that change icon, I want to select this tank option. You have several options. You have here the autoclave if you're doing autoclave calculations, or a pump, or any other. I want this one, the one that looks like a tank. And then click OK. And now we're going to change the name of this tank as utility water tank. Okay, and I'll put it here. And now I'm going to connect two streams. The first one is the return, going to this utility tank. And the other one is going to be a new stream that will be the makeup water. Okay, so we will click this white area and create a new feed. Okay, and of course we will have an outlet out of this tank. Let's rename these streams. This stream is the makeup water. And the outlet of this utility tank is going to be renamed to process. Okay, let's save. And we need to define the makeup water stream. Okay. Now this makeup water, as we all know, is the initial water analysis that we enter in our water analysis tab. This is the water analysis that I want to bring into my flow sheet. So how do I do that? So you'll see in the properties panel for this makeup water, in the right upper corner, it says show ionic input options. Okay, so that's a hyperlink, and we're going to click on it. And that's going to change the way how this ionic or this properties panel look. In this case, now what we're going to see is another section when it says ionic input with water analysis. So we need to select the source water analysis. And we go to select, drop down arrow, and you'll see that the water analysis that we created that is named water analysis -1 is here. So we're going to click on it. Okay. So when we click on it, then you will immediately see that the parameters were filled out with temperature and pressure. The total flow is not filled out because we need to define that. The water analysis is just for properties. It doesn't really matter which volume it is or how many grams or liters you have. So you need to define the total flow. For this total flow, let me see how much I had in my case. It's 100 metric tons per hour. So let's define that 100 metric tons per hour. And everything else, the composition of that water analysis, is brought by default. Okay. So that's how you enter the water analysis that's how you enter the water analysis into a stream that you previously defined. Okay. But now notice that the software is giving you an error. It's saying that these species that we are entering here, they are not present in the chemistry model. We never put them here in this chemistry model. So the software is saying, you didn't put them there, you better put them there because then I cannot do calculations. So what the software is saying is click here for possible resolutions. So we're going to click there and just clicking down here in this hyperlink. And it's going to tell you, it's going to give you two options. It's saying add the missing species to the unit's chemistry model or create a new chemistry model. For this example, we don't need to create a new chemistry model. I think that we can combine it with the previous chemistry model that we just created. So we're going to select the first option, add missing species to the unit's chemistry model. And that's it. So now if you go back to the chemistry tab, those components are added here. But those components are added as molecules. This comes back to the same, what we started from, the apparent molecular. All of those cations and anions now are represented by these molecules here in my chemistry model. Because my inflows in the chemistry model doesn't accept ionic inflows. Okay, so everything has been converted into molecules, and this is representing that specific chemistry that we enter with our water analysis. Okay, so now that we have the makeup water and now we have to process, I'm going to scroll up. We need to enter two more blocks. The next one is going to be the pump. Okay, but let's go ahead and run this just in case everything is amiss. So we need to catch any warnings or any errors. So everything looks fine. Click save. And now our next block is going to be a pump. We go to the library and click on the pump. And we're going to bring it up here, maybe to the left, a little bit to the left of this the simulation here that I have. Okay, so now I'm going to connect this stream to my pump, and you'll see there is something weird going here. So usually when you're doing a process, it assumes that you're going from left to right, and that's how the units think, that you go from left to right. But I want to go from right to left, but my input is here. So it's a little weird, but let's connect it. And what I am going to do here is I'm going to use this option that you see up here. Going just to rotate or flip this horizontally, okay? So that it just flips, and now my inflow looks that is going the right direction from right to left, okay? Okay, so we added that pump, and we need an outlet stream for that pump. Okay, so we add an outlet, and the outlet stream is going to be to heat exchanger. So this goes to my heat exchanger. The pump, I'm not going to change the name, everything is fine. Let's save. Now we need to define the pump, okay? So this pump is going to be, the specification in the parameter section is going to be discharge pressure. You have so many options here that are optional. You have, for example, the inlet area. You have the net positive suction head required, also optional. You have the motor efficiency. By default, we have put a number of 0.9. 0.9. The pump efficiency is by default 0.72. We also have a static head, that's optional. But what is very important for us is to actually define the discharge pressure. So for this discharge pressure, we are going to enter a value of 2. Okay. So really what we did here is the specification type, discharge pressure, and enter the discharge pressure of 2. Okay. We can run the simulation, and the next step is going to be add a heat exchanger. Okay. So we go and look for a heat exchanger. Where is it? Oh, there it goes. So again, we will add next to this pump in here. And probably this is also going to give you a hard time to connect. The process is always thought that it goes from left to right. So the inflow is going from left to right, right? Let me show you. So this is the logical thinking of the heat exchanger, but that's not how I want it. I want it to the left, going from left to right. So what I'm going to do is the same that I did for the pump. Select the heat exchanger and flip it horizontally using this icon up here. And now you'll see that the inlet here will be from right to left. And this, make sure that you're selecting the process stream inlet. The other one is the utility. It gives you the option to enter utility streams as well, but we are working with the process stream inlet tag. Okay, make sure that, or else it will give you an error message later. So click on the process stream inlet tab, not tab, but tag, and then also add an outlet for this stream from this heat exchanger. Also make sure that it says process stream outlet. Okay, so add another stream there, and then this is going to be the heated water. Okay, I hope that was clear. Nobody's behind. Okay, let's save. And now we need to define the specifications of the heat exchanger. That's the last specification we need to give to this simulation. So what we're going to tell the software is that we want a discharge temperature of, so in the specification type, click on here and go to properties panel, and on the spec type, select the option discharge temperature. You'll see that there are so many other options here for the heat exchanger. There is a temperature change, a heat duty, a temperature approach, the U area, and the vapor fraction. Okay. For this example, we're going to say that the stream is discharged at 35 degrees C, and that the pressure specification is not going to be the inlet pressure. The pressure specification is going to be the pressure drop. Okay, we're going to have a drop in the pressure within this heat exchanger of 1 atmosphere. So this is the definition of my heat exchanger. The flow geometry, you can always play with this, is a counter current or a co-current. For this example, we are using the counter current flow geometry option. So again, we have spec type, discharge temperature of 35 degrees C, a pressure specification of pressure drop, and a 1 atmosphere of pressure. Okay, so now the last step of this is, well, not the last step, but let's run this just to make sure everything is going well. But now what we need to do is to connect this heated water stream back to the cooling tower, right? Because this heated water is what we want to cool down. Okay, so what we're going to do is going to select this heated water and go to the cooling tower inlet, one of these seats. Okay, so now let's rearrange this. And this, obviously now you see that it's going to be a recirculation, right? We're going to have a recycle in this process. Let me save this. Okay, so as you remember when we were learning about reflux, we always need to make sure that we set a tear stream in order to run the simulation. And the software is telling you, you need to set a tear stream here because it's needed in order to understand what is the calculation order for this simulation. So we're going to click on this hyperlink again. What it says, click here, and it will tell us, okay, this is your reflux, this is your recycle, okay? You have a recycle loop here. Where do you want to put the tear stream? And I think that the most logical place will be here in the heated water. So what we're going to do is select the heated water, make sure that it has a double line, and then click OK. And again, you have your double line there, and you no longer have an error message here. Okay. Now, when you're working with cooling towers, and let me just fit this to center. When you're working with cooling towers, there are several properties that you want to know. So sometimes you want to calculate the cycle of concentration. So you will need to know, for example, the electrical conductivity of your blowdown compared to your makeup water. Okay, so for those properties, we need to turn them on. Some of these are optional properties, and we need to turn them on before we run the simulation. Okay, so we are going to click in any white area of this process in this flow sheet, and in the properties panel for the process, we are going to select the optional properties option. Click on this gray area, and okay, so click in there, and now these are all the optional properties that are set by default. Okay, sorry, that turn off by default. So again, this is because it takes a lot of it's expensive, and sometimes it just makes the simulation longer. So if you don't need some of these, there is no need to have them on by default. So click on the electrical conductivity and enable and say yes. This is what I want to see for this optional property, electrical conductivity. Okay, so then after this, now you can go ahead and run the simulation. Okay, we're almost done with this example. Okay, and it will take a little while because When we are doing recycles, again, we are tearing the stream here, and because we're dividing this stream, this recycle stream, it needs to match the composition of these now two different streams here, right? Because we're having this stream that comes here, and then there is a new stream coming here because we have separated it. And they need to converge. They need to be similar because it's the same stream. And you'll see this is all the iterations that they took in order to make this reflux or this heated water to match here when you tear the stream, when you divide the stream. Again, the reason why we tear the stream is because the software needs to know a calculation order. It needs to start from one block and then to the other block and then to the other block in a specific order, okay? When we have a reflux stream, the order is, the software doesn't understand which order to follow. It doesn't know if to calculate this first or this first or this first because it's having in common this flow or this stream here. So what we do is we divide the stream. We start with an initial value here for this heated water, and it starts going, now the calculation starts going in this direction. Cooling tower, blow down, utility water, pump, heat exchanger. And the software now needs to match this flow or this composition of this part of the heated stream with this part of the heated stream. And until they match, the software or the simulation converges. Okay.
Can I add something to this, Diana?
Sure.
Just quickly, when you look at recycles, the software is looking at the number, at the iteration number. So if the iteration is n would be, if you look at the tear stream and you look at the stream that's connected to the cooling tower, that would be the nth iteration. And it does n plus 1 iteration, and it looks at the stream that comes out of the heat exchanger. Then it looks at the stream that comes out of the heat exchanger, compares it against the stream that goes into the cooling tower and says, is my mass balance close here? Are these two streams the same? If it's not, I need to perform another iteration until, and it will continue going until the stream that comes out of the heat exchanger and the one that goes into the cooling tower are both equal in mass and component mass flow rates.
Right.
And then the other question I had for you is if you could tell us the air flow rate going into the cooling tower.
Yes, the airflow is, the total flow is 1,160 metric tons per hour. And that's the composition I had for CO2, oxygen, argon, and nitrogen.
And what was the makeup water flow rate?
And the makeup water flow rate was 100 metric tons per hour.
Thank you.
Okay. So we're almost done with this. The simulation converged. It took 43 iterations to match this third string here. But I want before, if you gave me 2 more, no, maybe 5 more minutes, and then we end the class, I want you to see one more report that I haven't talked about, and I think is very important. And that is the whole, the overall process balance report. Sometimes we run the simulation, the software is telling us it took 43 iterations, we're good, the simulation is completed, we're happy. And sometimes, yes, the software will complete the simulation, it will converge, but it's important to know if we are really matching the overall mass balance, heat balance, and species balance. So how do we check that? So we go to the menu bar and we click on the report. There are several types of reports. So we have seen the stream report, the block report, the multi-stream report, and the water analysis report. We haven't checked this one, the overall process balance report. So click on that one, add overall process balance report. And in here, it's going to tell you, it's going to give you 4 pieces of information. So you have, actually it's 3 pieces of information. You have all your inlets for flow and energy. Okay, you have the enthalpy or the heat. Okay, so it's saying total of inflows was 1,260. Okay, and the outlets were 1,260. So in and out, it matches. Now for the heat, it's saying you have minus 4.1 10 to the 11 as inlets, and for outlet you have minus 3.98. So that means that your block, there is a heat duty in your block. And if you add this minus 3.98 calories per hour, okay? I'm sorry, so you need to match, right? You need to have minus 4.1 10 to the 11 for the total inlets. So you need to match your outlets. So there is if you notice that you have a heat exchanger and it's producing this amount of heat, okay? So you will need to add this total amount of heat to this inlet, okay? And now you're matching that. If you do that, and if you have a calculator, then you will see that minus 4.1 10 to the 11 plus 1.24. I'm doing it here in my calculator. 10 to the 10, that will give you the minus 398 10 to the 11. So the heat is matching. That is good. So there is a final table here that is the material balance group, and this is what Zig was also mentioning. You need to make sure that you're not only matching the mass and the heat, you're also matching the species. Okay, so you need to check for these relative differences here. These relative differences is the error that you're having in matching the species going in and the species going out. Okay, so you need to make sure that what is going in, if you are entering 14.46 moles or metric tons of argon, that you're getting that much for that specific component, and so on. Sometimes when we're doing a calculation, and if you come here, you'll notice that there is a relative difference of 2, 3, 5, 10%. That's not good. That means that we need to go back to the process and maybe make sure that we are setting the recycle convergence options, or that we are increasing a tolerance in order to make sure that the final the material balance group is matching, that you're not having a significant difference in your element balance, right? And it's important. This is because this is an electrolyte software. We always need to make sure that we are matching all these species going in and going out. Okay, so that's what I wanted to talk about, the overall process balance report. And of course, we are done with this example, but of course you can always calculate here what is the efficiency of this process. When I was calculating the efficiency of this process, I got this from the literature. You can use these formulas here: range approach, the cycle of concentration. If you want to understand what is the electrical conductivity of your blow down for the cycle of concentration, you can always add a call out. Okay, you double click on your call out, then you will go to your thermodynamic properties and look for that electrical conductivity of the liquid one. Add it to your call out. Okay, so you have that electrical conductivity, and you can copy and paste the same report or the same table for the makeup water. Oh, it didn't copy my electrical conductivity. So thermodynamic property, electrical conductivity, okay. So you can compare the electrical conductivities and calculate your cycle of concentration. So when you calculate your cycle of concentration, I think I'm adding here a comment, text. I just use here my text label, cycle of concentration. I think that when you divide the electrical conductivity of your makeup water divided by the electrical conductivity of your blow down, it gives you a cycle of concentration of 1.2. Okay, and things like that. So you can start calculating and say, okay, what do I need to increase my cycle of concentration? Do I increase my blowdown? Do I increase my air content? And all of these things. And you can always run a sensitivity analysis to explore what to change and how does it impact your cycle of concentration. Okay, so with this, I will stop here and let me know if you have a final question, last question that you want me to go through. If you let me know if you didn't have any convergence issues. And with this, I will just end the class here. I will be giving to you all, providing to you all of these slides and all of these worked out examples that we worked in our class. And let me know if you always have questions. You can reach to me you can reach to us to our OLI.support email. Let me see if I have that slide here. Yes, this is the OLI.support email, or you can just contact me directly to diana.miller@olisystems.com. This is my direct number. Or you can always contact Jordan or Zeke that has been helping me here today. And thank you so much for your time. And I think that at this point, I will just give it back to you, Jordan, if you have any comments.
Sure. Yeah. I would just echo what Diana says. We're here to help. We've gone over quite a few examples. Not every one of them will be directly applicable to your case, but we also do have some case templates that we can send you to help you get started on various applications. So if you are interested, just contact me, Diana, OLI support, and we'll get back to you and we can help you get up and running. So we want to make sure that you get the most out of your OLI license. And if you have a service contract as well, make sure you get the most out of that. So thank you very much. And we'll be sending a survey with some feedback. We'd like to collect some feedback, how to make this better. And then Jira will be sending out certificates and recordings and all this associated material. But we're here to help. And thank you very much for your time and all the best, everyone. Have a great day.
Thank you. Bye-bye.
I have a question.
Sure, Yang. Go ahead.
Yes, maybe I need to share my screen. It seems I do not know what happened, but one of the stream name title for that stream is kind of